Hey everybody, welcome to our next conics section. We're going to be looking at section 10.4 and we're going to be looking at graphing ellipses today. So again, you should use graph paper for your notes because we're going to be doing a lot of graphing. And I wanted to remind you that ellipses come from taking a slice through your double cone that's tilted, but not so tilted that it touches either the top or the bottom of the cone, because that would create a parabola instead. So the ellipse is very similar to the slice for the circle, just tilted a little bit, which is what creates the stretched nature of it. So the first thing that we're going to do is we're going to talk about how an ellipse is actually created. And I've got a picture going in the upper right-hand corner so you can see what this looks like. But essentially an ellipse has two foci, and every point on the ellipse is equidistant from the sum of the distance from the foci. So in other words, we have d1 plus d2. The sum of the two distances from the foci, the two focuses, creates the distance to any point on the ellipse. So as you can see, that as a point gets closer to one focus, by definition, it gets further from the other so that the sum remains the same. So that's how you create an ellipse. And you can actually create one like using a string and two nails, for example, a couple strings and two nails. It's not actually that hard to do because you can just, as long as those distances, the sum of the distances remain the same, you can make it work. In terms of the formula for the ellipse, it's fairly complicated. I do absolutely need you to write these pictures in your notes. We've got two pictures here. One is for a horizontal ellipse. One is for a vertical ellipse. I'd like you to take a moment before I talk anymore. I want you to pause the video and copy down these two pictures and all the information embedded in them. All right, so I assume that if you resume the video, you've got these pictures written down. And you'll notice that an ellipse has a number of important points. It has two focuses, two vertices, and then also two things that are called co-vertices, which are essentially the vertices on the short axis of the ellipse, as well as its center. And it has what's called a major axis and a minor axis. And the major axis is the long way, and the minor axis is the short way for the ellipse. And for this class, we're only going to look at horizontal and vertical ellipses. When you get into pre-calculus, you'll look at rotating ellipses as well, so you'll be looking at them on diagonals. But all the principles stay the same. So we've got an equation for each of these. For a horizontal ellipse, our equation here is x squared over a squared plus y squared over b squared equals 1. And the important thing here is that by definition, a is greater than b. So for a horizontal ellipse, a is larger than b, which is what creates the major axis along the x-axis and the minor axis along the y-axis. Similarly, for a vertical ellipse, we've got essentially the same equation, x squared plus y squared equals 1, but now the b squared is under the x, the a squared is under the y, and because a is larger than b, that's what creates the vertical stretch instead of the horizontal stretch. So just for a second, let's think a little bit about why this equation makes sense. One thing I want you to notice here is that there's a plus sign in the middle. And the reason for that is that if you think about the ellipse, if you say you were to start at the top of the ellipse and work your way left, as your x value, as the absolute value of your x value gets larger, the absolute value of your y value has to get smaller because x plus y has to equal 1. And that's what creates the bounded nature of the ellipse. Instead of the ellipse like shooting off towards infinity, it has to wrap around on itself because x plus y has to equal 1, so as x gets larger, y has to get smaller. And obviously those are squared, which is what creates its circular effect. Similarly, if you think about the fact that a is larger than b, it makes sense, for example, that x squared over a squared plus y squared over b squared equals 1 would have a longer major axis horizontally, because as a gets really large, that allows x to also get really large, since x is being divided by a. And since b is smaller, it means y can't get as big as x could. So that's why the y part, the minor axis, is smaller, and the major axis would be bigger. Now, obviously, the center doesn't always have to be at 0, 0. And again, we would simply be adding in h and k, right? So we would have, for example, x minus h squared over a squared plus y minus k squared over b squared equals 1. Or we would have the same thing just with our a and our b switched for the vertical ellipse. So essentially the same, just subtracting h and k, just like we've done for every conic section. So the next thing we need to look at here is some way to relate a and b. Because a and b, between the two of them, they're what create the specific shape of every single ellipse. So we need an equation where we can relate a and b, so that if we have a, we can find b, and if we have b, we can find a. And the way we're going to do that is we're actually going to introduce, we're going to think about the focus C as well. And this is why the focus is relevant for the ellipse, as well as the fact that every point is the sum of the distance from the two foci. The focus is what allows us to relate A and B. So take a moment to sketch this picture into your notes again, and then resume the video. All right, so I want to talk about a couple things, and in doing so, our goal is to come up with an equation that relates A, B, and C. So I want to point out here that if we were to isolate a specific point, and let's look at this vertex right here. If you look at that vertex, we know the sum of the distances has to be the same for every single point on our ellipse. So we know that this distance right here, I'm going to call this distance d1, and this distance down here, d2. Now, if you notice, d1, because our vertex is at A, d1 equals A minus C, because A is the distance from the vertex to the origin, so the distance from the focus to the vertex is just A minus C. d2 equals A plus C, because it's the distance A from the vertex to the origin plus the distance from the origin to the focus. So the sum of those distances, d1 plus d2, equals A minus C plus A plus C, which would just be 2A, because the C's would cancel out. And that's important. And the reason that's important is because now we're going to look at how we can relate A, B, and C. And I want you to imagine for a second that I drew in a new triangle. I'm going to draw in a triangle from B to C, from the co-vertex to both focuses. And remember that the sum of those distances, d1 plus d2, has to be the same as the distance to the original vertex 0, a, which means that the sum of those two black lines has to be 2a. And that tells us that those two black lines have to be isosceles. These distances both have to be a. And we know it's an isosceles triangle because the two focuses are at C and negative C, so those distances have to be the same. So now that we know that that distance is A, I'm going to take that triangle and redraw it over here for a second. So our diagonal distance is A, our vertical distance is C, our origin is at 0, 0, and we know that our bottom distance, our horizontal distance, is B because it's going to the vertex. So now you can probably guess that we can apply the Pythagorean theorem here to relate A, B, and C. And specifically, we know that A squared equals B squared plus C squared. Now, typically, the way this is actually thought about generally is we subtract b squared from both sides, and generally we're going to use our equation to relate a and b, that c squared equals a squared minus b squared. So that's an equation that you're going to need because we're going to use that. Typically we know two of the three, and we need to find the third. Now students do sometimes get tripped up on this because it looks like the Pythagorean theorem, but not quite. So it's something that you really need to watch for. So let's take a look here at an example together. So imagine I wanted you to identify the center, vertices, covertices, and foci of the ellipse represented by this equation. And then I also wanted you to sketch it. So the first thing I would do is think about, okay, just by looking at this, do I know if it's going to be a horizontal ellipse or a vertical ellipse? And in this case, because 36 is less than 64, the 64 is under the y, which tells me that the general structure of this ellipse is that it's going to be vertical. So I always put that in the back of my mind first because it helps me to think about these problems. So let's see if we can identify A, B, and C. So we want to know our A, B, and C values so that we can come up with our center, vertices, foci, and ellipses, and covertices. So we know in this case that A is the square root of 64, so A is going to be 8. B is the square root of 36, so B is going to be 6. And C we know because we know that C squared equals A squared minus B squared. So in other words, we know that C squared equals 64 minus 36 because 64 is A squared, 36 is B squared. So C squared C equals the square root of 28. Or in other words, C equals 2 root 7. So now that we know A, B, and C, we can identify all the things that are asked for in this problem in order to graph it. So I'm going to start with our center. And because H and K are both 0 in this case, our center is at 0, 0. So I'm going to put in a point at 0, 0. We know our vertices have to be along the y-axis because we said that our ellipse was vertical in this case. And our A value is 8. So our vertices would be at 0, 8 and 0, negative 8. So I'm going to put those in as well. So 8 and negative 8. And then our covertices are going to be horizontal for this problem. So our covertices would be at 6, 0 and negative 6, 0. So I'll put those in too. And then we also know that our foci, so our foci are always along the major axis, right? So in this case, they're on the y-axis. So our foci are going to be at 0, 2 root 7 and 0, negative 2 root 7. And 2 root 7 is about, it's about 5.3 approximately. So I'm going to put in my foci as well, as best I can. And then I'm going to try to draw in my ellipse, and hopefully yours will look better than mine. But the idea is that it should look as much like an oval as you can do. So this would be all the key information as well as the picture for this ellipse. So let's look at one more example together here. So again, I want to identify the center, vertices, covertices, and foci of the ellipse. And I want to sketch the graph. But notice here, this one's a little bit different because by definition, the equation for an ellipse has to equal 1. And this one doesn't. Which means the first thing that we have to do is make it equal to 1. So I'm going to divide everything through by 16 to get our new equation, which would be x minus 3 squared over 16 plus y plus 1 squared equals 1. And now we're in the form where we actually have an elliptical function in standard form. because we've got something squared plus something squared equals 1. So we're going to start the same way we did the last problem, which is we need to identify A, B, and C. And in this case, A is 4, B is 1, because it's divided by 1 when it's not showing. And C is going to be, well, C squared equals A squared minus B squared, so 16 minus 1, which equals 15. So C is going to be the square root of 15. The other thing we want to think about here is this going to be a horizontal ellipse or a vertical ellipse? And in this case, because A is under X, we know that just roughly speaking, our ellipse is going to be horizontal, right? So now let's see if we can come up with all the critical information. So our center for this one is going to be at 3, negative 1, because our H value is 3 and our K value is negative 1. So I'm going to start by putting in our center. I'll put that in right there. And then our vertices. So our vertices in this case are going to be horizontal. So they're going to change the x coordinate. And specifically, they're going to go up by 4 and down by 4 from the center. So our vertices would be at 7, negative 1, and negative 1, negative 1. So my two vertices here would be at 7, negative 1, so 1, 2, 3. So 7, negative 1, and negative 1, negative 1. Our co-vertices, those would change the y coordinate in this case. And our co-vertices are going to go up and down by 1. So we're going to be at 3, 0, and 3, negative 2. So we're going to go up by 1 and down by 1. You can see that this is going to be a much skinnier ellipse in this case. And then finally, our foci are going to be along the major axis, so the horizontal axis for this problem. And they're going to go up and down by the square root of 15. So we would have 3 plus the square root of 15, negative 1, and 3 minus the square root of 15, negative 1. And so you just need to think about, well, the square root of 15 is a little bit less than 4, right? Because it's a little bit less than the square root of 16. So our foci would be just inside, in this case, of our two vertices. And then if I go to draw in our ellipse, hopefully yours will be much better than mine was, but that gives you the rough shape for what that would look like. So this brings us to the end of our video for 10.4. I know there's a ton of information in here, but once you practice it a few times, I think you'll start to get the hang of finding all the information and then sketching the graph of the ellipses. As always, use graph paper for this because clearly you're graphing, and let me know if you have questions.